Okay, today we start learning about random walk on network. So first we recall a notion that will be used for today. It is reversible. So we introduced this notion on the first lecture. A Markov chain is reversible if there exists a probability measure. A probability measure pi satisfies the detailed balance equation. This is the definition for reversible. And in the first lecture, we showed that if such a probability measure exists, then this pi has to be the stationary measure. And in particular, if we know that the Markov chain P is irreducible, then the stationary measure is unique. So this is the unique stationary probability. And next, we also derived that if such a measure exists, then the time reversal of the Markov chain has the law of itself. So the time reversal has the same law as it itself. Okay, so this is the notion related to reversible Markov chain. And today we will first introduce what is a network, and then the random walk on the network, and we will show that the random walk on the network will always be reversible. And then we introduce what is voltage flow, current flow, and finally we introduce what is the effective resistance of the network. Okay, so network. A network is just a graph. It's an n-oriented connected graph, G. So V is the set of vertices, E is the set of edges. And it is a network, so there's more than a graph. So a network is a graph with a collection of non-negative integers. So on each edge, there is a non-negative real number, CE. And so a network is just a graph with this collection of non-negative numbers. And in this definition, we say that CE is the conductance of the edges. And we also write RE is the inverse of the conductance. And we call it as the resistance of the edge. So this is a network. A network is just a graph with a collection of non-negative numbers. Okay, and then a random walk on the network. So recall that when we introduced reversibility, we introduced random walk on the network when the network has just a unit conductance. So it is just a random walk on the graph. So this is a graph. And the random walk on this graph is once we arrive at a vertex, we count how many neighbors we have, and then we jump to one of the neighbors uniformly. So this is a simple random walk on the graph. And now we have a network. So the random walk on this network is almost the same as a simple random walk on the graph. The only difference is when we jump to the neighbor, the proportion of this neighbor is the probability to why we want to jump to this neighbor is proportional to this conductance. So for the random walk on the network, the transition matrix Pxy is proportional to the conductance. Okay, so Cxy means xy given edge. So Cxy is the conductance on this edge, and Cx is just a normalizing constant. Okay, so we have a network and we give the transition matrix. Of course, this transition matrix uniquely determines our Markov chain on this random walk, on this graph. And now we can see that because of this transition matrix has the expression in this way, suppose we are at the vertex x, and this is our vertex y, and we will jump to the neighbor. The probability that we jump to this neighbor is proportional to the weight on the edge. So this is just almost the same as the simple random walk on the graph. And the only difference is there is a weight when we jump to the neighbors. So this is also called weighted random walk on the network. And for this weighted random walk on the network, we can easily check that there is a probability measure that is irreversible. So lemma, we define a measure pi in the following way. So in this way, we define a measure. And then this measure pi is reversible. Okay, so a quick proof, just to recall all the notions related to reversible. So when we want to show pi is irreversible, first we need to show that pi is a probability measure. So we need to show that the total mass of this pi equals 1. So what's the total mass? This Cg is a universal constant. We put it in front. So this is the total mass of this pi x. And by definition, this summation equals Cg. So the total mass is 1. And then we need to show that pi satisfies the detailed balance equation. So we need to show that pi x times pxy equals pi y times pyx. So now let us check what is pi x times pxy. So by definition, this is pi x. And this is pxy. And here we see that cx are canceled. So what we have is Cg, Cxy. And now, since this conductance C is symmetric with respect to two vertices because it's only defined on the edges, and we can see that it is exactly the same as pi y times pyx. So pi satisfies detailed balance equation. And here we have shown that pi is irreversible. After we show this pi is irreversible, in fact, what we know is for the weighted random walk on the network, it is reversible. And this means that the time reversal of this weighted random walk on the network has the same law as it itself. Okay, so this is the random walk on the network. Next, we will introduce voltage and flow. Before we introduce what is a voltage, we need to introduce a related notion. It's called harmonic function. So for harmonic function, so here, just to introduce several notation. Our state space is always finite. And now this is P is the transition matrix. And we always assume it is irreducible. And a function h defined on omega to r, we say that it is harmonic at a vertex if it satisfies the property that we jump to the neighbors, and then the average of this after jumping is the same as the original value. Okay, and then Xn is just a weighted random walk on this Markov chain. So weighted random walk on the network, or we call it as a Markov chain with transition matrix P. B is a subset of the state space. And now we can define the first heating time of this Markov chain. Tau B is the first time that the Markov chain heats the set B. And then the conclusion about harmonic function is we fix a function HB defined on the subset B. And then we define a function hx in this way, and this function h is the unique harmonic extension So this h is the unique harmonic extension of HB. So first, a few words on the definition of this hx. So this means our Markov chain starting from vertex x. And then we know that at time tau b, this x will hit a point in B. So HB is the value of this function at that point. So this is well defined because this HB only defines on the set of B. And so hx is the expectation that the Markov chain starting from x. And we take the expectation of HB when the Markov chain hits a point in the B. And we say that H is the unique harmonic extension of HB. So this statement has three small arguments. So first, it is the extension of HB. It means that H equals HB for x in B. So this is the meaning for this is an extension of HB. Okay, and then it is a harmonic extension of HB. It means that for x outside B, it is harmonic. And the third argument in this statement is the harmonic extension is unique. Okay, so from the statement here, in fact, we need to prove three little arguments here. Okay, so first, why H is an extension of HB. So why for x in B, what's the value of hx? So by definition, hx is the expectation of HB when the Markov chain hits B. And if x is in B, so this means our Markov chain starting from x, and this is already a vertex in B, so our tau b equals 0. And of course, x tau b equals x, and over hx is exactly hbx. So by definition of this h, we know that it coincides with hb on the set of B. So this is the proof of the first argument. Second, we show that for a vertex outside B, this h is harmonic. So for x outside B, Then what happens to this hx? Since x is outside B and tau B is the first heating time of B, we know that it has to be greater than 1 because we start from a vertex outside B. So at least tau B is 1. And now we divide into different cases for what happens in the first step. So suppose first step, we jump from x to y. So we just divide the event according to what happens to the first step. And now let's check this conditional expectation. We know that this is a Markov chain. Markov chain starts from x, and the first time we jump to y. And then we want to calculate what's the expectation for the time that the Markov chain hits B. So because this is a Markov chain, we know that in fact this is just a new Markov chain starting from y. And tau B is also the heating time of this new Markov chain hitting the set B. So this part, we know that it is exactly the same as a Markov chain starts from y. And we calculate the expectation. And this is exactly the same as definition for hy. So what we have here is when x is outside B, hx is harmonic at x. Okay, so this is the second argument. And then finally, we need to show that the harmonic extension is unique. So recall that in the first lecture, we have shown that a harmonic function has to be constant. In that case, what we proved is the harmonic function is harmonic everywhere in the graph. But now we have a boundary set. So this B, we can view it as a boundary set of the graph. And the theorem says we fix the boundary point and the function is harmonic inside, then it has to be the unique. So it's the same as the harmonic function we learned from complex analysis. So this is different cases from what we proved in the first lecture. So in that case, there's no boundary point. So harmonic function, if it is harmonic everywhere, then it has to be constant. But now we have a boundary. So then the harmonic function is uniquely determined by the boundary values. So why it is unique? And you can also check that the proof is also similar as before. So we show that it is unique. It is sufficient to show that if f is 0 on B and is harmonic outside B, then f has to be 0 everywhere. So it is sufficient to show this argument because if we prove this argument, then if there are two harmonic extensions, we can just take the difference between the two harmonic extensions, and then the difference satisfies this relation. So the difference is 0 on B and harmonic outside B. And from this argument, we show that the difference is 0 everywhere. So this means these two extensions has to be the same. Okay, so it is sufficient to show that for a function f, if it is 0 on B and harmonic outside B, it has to be constantly 0. Okay, so why this is true? So the idea is the same as before. We look at the vertex that the function attains as a maximum of the whole space. And then if a vertex is in A and x is not in B, then we know that this f is harmonic. It will harmonic at x. Since it is harmonic at x, we know that we have this relation. And here, if pxy is strictly positive, we know that fy also needs to be the max. This is what we proved in the second lecture, I think. So now, in the first step, what we have is, if x in A, x not in B, and pxy is strictly positive, so combining these three conditions, we know that fy also equals the max of the function. So this is the first step. And then, for any y in the states okay. And then we need to show that this function is constant. Okay, since p is irreducible, we know that there exists a sequence such that it is jumping from vertex x and to a vertex b. So since p is irreducible, we know that there exists a path. So this path jump starts from x, and it jumps along vertex outside B, and at some first time it jumps inside B. And then we can apply the argument we have there to show that, in fact, fx1 equals the max, and fxn also equals the max. So just to repeat the same the argument in the first step. However, we also know that xn is inside B. So xn inside B, because we assume that f is 0 on B. So we know that fxn is 0. So combining these two, we know that the max of f is 0. So f is negative everywhere. So f is always negative everywhere. And then we apply the same proof for minus f. And we can also show that f has to be positive everywhere. And combining these two, we know that f is constantly 0 everywhere. So this shows that a harmonic function is uniquely determined by its boundary value. Okay. Okay, so this is a basic fact about harmonic functions. Then we can introduce what is a voltage. A voltage is just a harmonic function on the set of vertices. On the set of vertices, but we remove two vertices. So one is called A, the other is called Z. So for a network, usually we will specify two vertices. One is A, we call it is the source, and another one, Z, is called the sink. And the voltage is just a harmonic function on the set of vertices except the source and the sink. And here before, by the theorem for the harmonic function, we know that a voltage is uniquely determined by its boundary value. So a voltage W So this function, since it is harmonic, it is uniquely determined by the boundary value WA and WZ. Okay, later you will see that this voltage is actually the same notion you have learned from physics. Voltage. And the next notion is called flow. Okay, a flow on the network is just a function on our entity edges. So a flow theta from A to Z it is a function on our entity edges, and it satisfies the following three properties. So it's a function and it satisfies the following three properties. First, it is antisymmetric. So if we reverse the orientation of this edge, then the flow is multiplied by -1, antisymmetric. And second, the divergence at every vertex equals 0. So the divergence of a flow at a vertex is defined in this way. So this is the divergence of a flow at a vertex, and it is 0 everywhere except the source and the sink. And this property is actually the property we call the knot law in physics. So it means that for a vertex outside the source and the sink, we always have flow in equals flow out. So this is the knot law in physics language. And the third property, the divergence at the source is positive. So of course, this means that at the source, we have flow out. And for vertex outside the source and the sink, flow in equals flow out. And finally, at the sink, we only have flow in. So this is a network. We have a source, so there's a flow out. And then finally, all the current will flow to the sink. Okay, so this is flow. It's an antisymmetric function defined on our entity edges. For vertex outside source and the sinks, the flow in equals flow out. And for the source, we have positive divergence. And here we can also show that, in fact, the divergence at the sink is minus the divergence at the source, so it is negative. And for this flow, we define that the strength of the flow is defined as the divergence at the source, so it is non-negative. And we call a unit flow if the strength is 1. Okay, so this is a flow. Now we introduce the voltage, and we introduced what is a flow. And then what's the relation between these two? Okay, a voltage will naturally introduce a current flow. So it will introduce a flow, and for this flow, we call it is the current flow. Okay, a current flow so given a voltage, we define a flow in the following way. we can you can check by yourself that we define a function in this way, then it is anti-symmetric on the oriented edges. And at every vertex outside the source and the sink, the divergence equals 0. And at the source, the divergence equals WA. And at the sink, so it is positive, and at the sink, it is negative. So you can check directly that we define a function in this way, then it satisfies the definition for a flow. And we call this is the current flow associated to the voltage W. And for this current flow, it satisfies several properties we already know from physics. So first is called Ohm's law. So Ohm's law tells us the resistance times the current flow equals the difference on the voltage. This is immediate from the definition because we just multiply resistance to both sides. Resistance is 1 over the conductance. So now it's just a definition of this current flow. This is Ohm's law. The second property is called the cycle law. Okay, for the cycle law, it means that if we have a sequence of oriented edges and the sequence of edges form a cycle, then the resistance times the current along this cycle equals 0. So we can check this property directly because this just so suppose EJ has the starting point xj and has the ending point xj plus 1. Then we know that resistance times the current flow equals difference of the two voltage. And then we sum it over one cycle. Of course, this will give a 0. Okay, current flow satisfies cycle law. So these two properties are almost immediate from the definition. And then the next property is not trivial. So it says that, in fact, the cycle law characterizes the current flow. So by this, we mean that if we have a flow, it satisfies cycle law, then it has to be the current flow. So if theta is a flow satisfying the cycle law, and it has the same strength as the current flow, then it has to be the same as the current flow. So this is the first non-trivial property for the current flow. So it says that, in fact, the cycle law characterizes uniquely the current flow. So if we have a flow, and if we can show that it satisfies the cycle law, then we prove that it is the current flow. Okay, so why this is true? Want to show that the cycle law characterizes the current flow. So what we need to show is the difference between theta I is 0 everywhere. So it is sufficient to show that this f is 0 everywhere. And here let us check what is the difference between the two. So f is the difference between theta and I. So first we can see that f satisfies not law. So first we know that for any flow, it satisfies the not law except the source and the sink. And now we take f as the difference between these two flows. Then for the vertex outside source and the sink, we know that it has to satisfy the not law, so flow in equals flow out. And also at the same time, at the source, we know that the flow, the divergence of this guy equals 1, equals the strength. And the divergence of this guy also equals the strength. And since we assume that the strengths are the same, so this F also satisfies the NOT law at the source. And then in the same way, we can also prove that it also satisfies the NOR law at the sink. So it satisfies the NOR law in the same way as the flow. And then more than that, it satisfies the NOR law for all the vertex. Okay, so this is the first property F satisfies. Second, since we assume that this theta satisfies cycle law, and we already know that the current flow satisfies cycle law, so this F also satisfies cycle law. Okay, so this is the two properties that F satisfies. And now we want to show that F is 0 everywhere. So we prove by induction, by contradiction. So assume that F is strictly positive for some edge, E1. And since F satisfies NOT law, we know that this E1 must lead to another edge such that F also is strictly positive. And then we repeat the same procedure. So E2, F is strictly positive. And since F satisfies the NOT law, then E2 also leads to another vertex, another edges, E3, such that F is strictly positive. So in this way, we have a sequence. And along this sequence, F is strictly positive on every edges. And this sequence is the ending point is E1, is the starting point of E2, and the ending point of E2 is the starting point of E3. So this is how the sequence goes. However, we know that the state space is finite. So the set vertex V is finite. This tells us this infinite sequence has to revisit some vertex. And since this sequence has to revisit some vertex, so maybe this sequence is like this. So maybe the sequences look like this, but we know that the set of vertices is finite, so this sequence has to revisit a vertex. And once it revisits a vertex, then we have a resulting cycle. And for this resulting cycle, by the definition of the sequence of edges, we know that it is strictly positive along all the edges. So this resulting cycle violates the cycle law. And we get a contradiction here. So if F satisfies both NOT law and cycle law, then it is impossible for us to have some strictly positive edges. Okay, so this shows that a current flow satisfies almost law, cycle law, and also the cycle law uniquely determined the current flow. And then we can introduce what is effective resistance. So effective resistance for a network, and we fix the source and the sink. And the effective resistance between A and Z is defined in the following way. Suppose W is a voltage, and I is the corresponding current flow. Then we define the effective resistance as the difference of the voltage at the source and the sink, and then normalized by the strength of the current flow. So first, one remark: if our network just has one edge and the two vertices are A and Z, then this is exactly defined in the same way as Ohm's law. So resistance times the current equals the difference of the voltage. So this is the first remark. The second remark is this effective resistance is well defined. So what's this mean? Because when we define this effective resistance, this W voltage is, there are infinitely many choices of the voltage. And of course, each one has a corresponding current flow. So if we change to another voltage, why this ratio is the same as this one? So we need to show that this definition is well defined. So suppose W tutor is another voltage. And I tutor is the corresponding current flow. Since we know that this W and W tutor are harmonic function, and their value are uniquely determined by the two endpoints, W tutor A and W tutor Z. So there are only 2 degrees of freedom in the definition of these harmonic functions. So we know that W tutor has to be linear in W. So there exist 2 constants, lambda and mu, such that W tutor is linear in W. Because there are the total freedom of degree is only 2. So this 2 has to satisfy this relation. And the constants lambda and mu can be just uniquely determined by their boundary values. So since W tutor has this relation with W, we know that the corresponding I tutor equals lambda times I. So then if we define the effective resistance in the right way, in the way of the right hand side, then we say that this constant lambda will cancel in the denominator. So it is exactly the same as W normalized by the strength of the current flow. So here we have shown that the effective resistance here is well defined. Okay, and now we will have a break, and after the break, we will show what's the relation with effective resistance and the random walk on the network. Okay, we restart with effective resistance. So up to now, we introduced what is effective resistance, and it's defined from a voltage and the corresponding current flow. And in the next theorem, we will show why we are interested in this quantity, because it is closely related to the escape probability of the random walk on the network. So the relation between the two is so this is the escape probability of the random walk on the network. So it means that we have a random walk, it starts from A, and we want to calculate what's the probability that it hits Z before going back to A. And this escape probability is exactly proportional to the inverse of the effective resistance. So this is the relation between escape probability and the effective resistance. So before we prove this theorem, one remark is this relation is very interesting because for the network, we can calculate the effective resistance directly. Suppose we just have a network. We put a voltage 1 at A and attach Z to the earth. And then we can measure what's the effective resistance of this network. And this relation tells us, once we measure what is the effective resistance, it tells us what is the escape probability of the random walk. And another remark is, for the network, we know that if we do some operation to the network, then we will increase or decrease this effective resistance. And from the relation, we know that this operation also increase or decrease in the reverse way as the effective resistance when we do the operation to the network. So in fact, it is not obvious at the first why, say we do some operation to the network, why it increase the escape probability or decrease it. But from the relation here, we can clearly check the relation here. Okay, so this is the importance of this theorem. It tells us the relation between effective resistance and the escape probability, and why this relation is true. So how to relate these two quantities together? So consider the following two functions. So this is a function defined on vertex. So it's from x and to the probability that the Markov chain starts from x, and then we calculate the probability that it hitting z before a. This function is harmonic. Except a and z. And we know that it has value 0 at a, and the value 1 at z. So this is a harmonic function, and we also know the two boundary values of this function. The second class function we considered is so W is the voltage on the network. And this function, we also know that this is a harmonic function outside a and z, because W is just a harmonic function outside a and z, and here it's just a linear combination of W. So this is a harmonic function. And we can check that it has value 0 at a, and the value 1 at z. So now we have two harmonic functions, and they have the same boundary value. By the uniqueness of this harmonic extension, we know that these two functions has to coincide. So combining these two, we know that for any x, we have so here we can already see the importance of the relation. This is the escape probability, and here's just some harmonic function. So once we know how to calculate the harmonic function, it tells us what is the escape probability. So the left-hand side is not so direct to calculate at the beginning, but the right-hand side is much easier to calculate. Okay, so this is the relation between escape probability and the voltage. And now we want to show the probability the Markov chain starts from A and hit Z before going back to A. And now what we do is we divide the probability according to what happens to the first step. So for the first step, the Markov chain jumping from A to X. And then the Markov chain is just a new Markov chain starting from X. And then we calculate the probability that tau Z is less than tau A. So because we already jumped once, so the first return time become the first hitting time now. And by the above relation, we know that this is PAX. And what is P by definition? It is just the conductance, normalized conductance. And here we are summing over X. So this CA and WA minus WZ has nothing to do with X. We can just put them outside the summation. And here we see that this is the conductance times the difference on the voltage. So this is exactly the current flow. And now we are summing over all X. X is a neighbor of A. So this is the definition of divergence of current flow. And the divergence of the current flow at the source A is exactly the strength of I. So strength of I divided by the difference of the voltage is the effective resistance. Okay, so this proves the relation between effective resistance and escape probability. And next, we will see several applications of this relation. Okay, so first we introduce the 3 operations to simplify network. Probably these 3 operations you already seen in high school. So for a network, we have 3 operations to simplify a network. So for this 3 operation, after this operation, we know that the voltage and the current flow is unchanged. So the first operation is called parallel law. So this parallel law means that if we have 2 edges and they share the same endpoints, so this is E1, this is E2, and this edge has conductance CE1, and this edge has conductance CE2. And the operation says, for a pair of 2 edges in this way, we can replace them by 1 edge. And the resulting conductance is just CE1 plus CE2. Then for the other part of the network, nothing is changed. So voltage and the current flow is the same as before. So this is the first operation, parallel law. So we can replace 2 parallel edges by 1 edge, and the conductance is just the sum of the 2 conductance. And the second operation is called series law. In series law, it means that we have 2 edges. They share the same vertex here. And for this vertex, there's no edge, other edges connecting to it. So if 2 edges has the position in this way, the first one has resistance R1 and the second one has resistance R2. Then these 2 edges can be replaced by 1 edge. And the resistance is just the sum of the 2 resistance. So just to remember that here's the sum of the 2 conductance and here is the sum of the 2 resistance. So this is series law. So after this operation, we can show that the voltage, all the conditions of this network is unchanged outside this small part. Okay, the third operation is called gluing. So the third operation says, in the network, so it can be something very complicated. If we have 2 vertices, and these 2 vertices, we know that they have the same voltage, then we can glue them together, then nothing changes to the network. So if they have the same voltage, then we can just glue them together and nothing changes in the network. So this is the third operation, gluing. So this is three operations, parallel law, series law, and the gluing. Tell us this, they simplify the network, but nothing changes. So no change to the voltage, no change to the current flow. And then the first example is we can use this three operation to simplify a network. And finally, we can calculate what is the voltage of this network. And this will give us the relation to the escape probability of the random walk. Okay, first application. Consider a biased random walk on the interval. So this interval has n plus 1 vertex. It's just a line, stand along a line. So this is 0, 1, 2, and this n. So this is a network, and the conductance on the edges is given by this relation. So we fix a constant alpha. The conductance on the first edges is alpha, and the second is alpha squared, and alpha cube, and finally this is alpha n. So here we see that if alpha equals 1, then this is just a network with unit conductance. And then the random walk on this network is just simple random walk on this interval. But now, if alpha is different from 1, then this is what we call the weighted random walk. So suppose if alpha is greater than 1, then we have the property that we want to jump to the right more than jump to the left. Okay. So the conclusion is, now we can calculate the escape probability. So the random walk starts from k, starts from vertex k, and we want to calculate what's the probability that it hits big N before 0. So here again, if you still remember what the model we introduced in the first lecture is called the gambler's ruin. So in gambler's ruin, in fact, we're just calculating, we start from some initial amount of money in the purse, and this is the probability for winning the game. And in there, we showed one way on how to calculate this probability, if you still remember. And today, in fact, we introduced another way to calculate this probability by simplifying the network. So first, now we want to calculate what's this probability. From the relation we showed here, we see that if we have a voltage on this network, and this is the source, this is the sink, then we know that this probability equals this function. So this is what we get from here. So now we only need to calculate what's the harmonic function W here on this network. Okay, so what's the harmonic function? What is the voltage? This is our network. And now we want to use these three operations to simplify this network. We know that this three operation doesn't change what happens to W0, Wk, and Wn. So what we do is, for this pair of edges, we use a series law. Then the resistance just replaced by summing of the two. So we just use series law. Use series law to this network. So what we do is we apply the same rule to all the edges from 0 to k, and apply the same rule for all the edges between k and the big N. So what we have is, then the network can be simplified as the network only has 2 edges and 3 vertices. And the resistance here is because of this 3 operation, we know that the voltage on this network is exactly the same as the voltage on this network. So now for this network, suppose I is the current flow. Then what we know is W0 minus Wk should be the resistance IR1 times the current flow. And W0 minus Wn is the resistance times the current flow. And then this current flow cancels in the 2 parts. So what we have is the probability is just R1 over R1 plus R2. And here R1 is this one, R2 is this guy. So this tells us the escape probability. And here we see that if this calculation is much easier than what we did in the first lecture. Okay, so this is the first example. The second example, we can calculate the escape probability of simple random walk on a binary tree. First, just give 1 page about the precise meaning of a binary tree. So a tree is a connected graph with no cycles. A rooted tree just has a distinguished vertex. We call it as the root. The depth of a vertex V is this graph distance to the root. So now we just draw this tree according to their depth. So this is the root. So this is root. And these 2 vertices are of depth 1. And these 4 vertices are of depth 2. A leaf is a vertex with degree 1. So here in this graph, we can see that these vertices are the leaves. So because they only have degree 1. So this is just the general definition for a tree. And then a rooted binary tree of depth k is just a tree such that the root has vertex 2. And then for any vertex in the middle has degree 3. And for the vertex at the leaf at the bottom line, they have degree 1. So this is just in the usual way we can imagine for a binary tree. So this is a rooted binary tree. And for this rooted binary tree, suppose that on each edge we just put a unit resistance, and then we have a network. And for this network, we can calculate that there are 2 to the power k plus 1 minus 1 vertices, and the number of edges is n minus 1. And suppose B is the set of leaves, and now we can calculate what is the effective resistance from the root to the leaf. And in turn, this effective resistance will give us the escape probability of the random walk on this network. So think it for 5 seconds, how to calculate the effective resistance from the root to the end. Okay, so first, since this graph is highly symmetric, we can see that the vertex at the same level have the same voltage. The vertex on this level all have the same voltage. So since they have the same voltage, by gluing, by the third operation, we can glue all these vertex together. So this tree has the same voltage as this guy. It has the same voltage as this guy. So from here to here, by gluing, and then for this pair of edges, we can apply parallel law. So parallel law tells us, so this is the unit resistance. Then this pair of edges can be replaced by one edge. and the resistance become 1/2. So 1/2. And for the 4 edges here, we apply a parallel law again. They can be replaced by 1 edge, and the resistance become 1/4. And these 8 edges can be replaced by 1 edge, and the resistance is 1/8. This is a parallel law. And then here we say that we can apply series law. So this pair of edge can be replaced by 1 edge, and the resistance is the sum of the 2. And then we repeat the same procedure. What we see is these edges can be replaced by 1 edge, and the resistance is 1/2 plus 1/4 plus 1/2k. And for this guy, for all this operation, we know that the effective resistance is unchanged. And for this guy, the effective resistance is exactly the resistance on this edge. Okay, so this tells us how to calculate the effective resistance of this binary tree. And this effective resistance also tells us the escape probability of the random walk on this network. Okay, so this is the second example. And finally, we conclude today's lecture by showing that the effective resistance gives us a metric structure on the state space. So before this theorem, we always fix the source and the sink. And now in this theorem, we want to change the source and the sink. And here we see that the effective resistance satisfies triangle inequality. And since it satisfies triangle inequality, in fact, the effective resistance gives us a metric structure on the set of vertices. So the effective resistance satisfies triangle inequality. Okay, so why this is true? To calculate the effective resistance, just a quick recall, the effective resistance is the difference of a voltage normalized by the strength of the current flow. So if we assume that the current flow is the unit current flow, then this strength is just 1. So the effective resistance just becomes the difference between the two voltage. So assume that I1 is the unit current flow. From X to Y. And W1 is the corresponding voltage. Maybe here. Then we know that the effective resistance between X and Y is Wx, W1x minus W1y. And then assume that I2 is the unit current flow from Y to Z. And W2 is the corresponding voltage. Then we know that the effective resistance is W2y minus W2z. So here I've done nothing, just write down the quantity in the right-hand side. And now let us check what's the relation to the left-hand side. So now we define W is the sum of the two. I is also the sum of the two. So first, we can check that W is a voltage from X to Z. So why this is true? Because so W is the sum of W1 and W2. Outside the vertex X, Y, Z, both of them are harmonic function. So W is also harmonic outside X, Y, and Z. So we only need to show that W is also harmonic at Y. So we only need to show that So we only need to check what happens at vertex Y. So at vertex Y, and Y it is harmonic. So we need to check this expression is the same as WY. Oh no, harmonic means, all right. So why this is true? W is W1 plus W2. So for the right-hand side, and we know that W1 is the harmonic function from X to Y. So this is exactly the divergence of the current flow at Y. Divergence of I1 at Y. And this is because W2 is the harmonic function from Y to Z, and we are summing over Y. So this is exactly the divergence of I2 at Y. And here, since we assume I1 and I2 are the unit current flow, so this guy equals plus 1, and this guy equals minus 1. So the sum of the two is 0. Wait, 0? So what's wrong here? Great. Sorry. So we want to show it is harmonic. So why this equation holds? So we divide, subtract both sides to to WY. So we want to show this expression equals 0. And for this expression, we plug in W1 and W2. And the first expression corresponds to exactly the divergence. And the second expression corresponds to the divergence of I2 at y. And now we can conclude that because this is -1 and this is +1, so the sum of the two is 0. So this shows that W is also harmonic at y. And since it is harmonic at y, we know that it's just a harmonic function outside x and z, so it is a voltage from x to z. And since W1 is just the resistance times I1, W2 is resistance times I2, so of course, I is the corresponding current flow for W. And moreover, we see that I is the unit current flow because the divergence of I at x equals the divergence of I1 at x and the divergence of I2 at x. And for I2, we know that the divergence outside y and z, flow in equals flow out. So this guy is always 0. And for I1, x is the source of I1, so this one is 1. So here we have shown that if we put W equals W1 plus W2, then W is the voltage, and the corresponding I is the corresponding unit current flow. Okay, so W is the voltage, I is the corresponding unit current flow. And then we can conclude that the effective resistance from x to y, it is exactly Wx minus Wy. So now we know that this is the right-hand side, this is the left-hand side. We only need to show that the left-hand side is less than the right-hand side. So plug in the, because W is W1 plus W2, what we have is so this is the left-hand side. Left-hand side. And the right-hand side is the sum of these two. So this is Z, yes. Okay, the right-hand side is the sum of these two. Okay, so y, left-hand side is less than right-hand side. So this term are the same. This term are the same. So we want to show this guy is less than that guy. So first observation is W is harmonic on V minus X and Y. And for harmonic function, we know that the harmonic function attains its max and the minimum on the boundary. So this tells us W1Z has to be between W1X and W1Y. Because this is harmonic function, we know that it attains max and the minimum on the boundary. And then the boundary only has 2 points, X and Y. And one is bigger and one is smaller. So W1 is the max, W1Y is the minimum. And W1Z has to be between them because of the because this is a harmonic function. So here we already show that minus W1Z is less than minus W1Y. And then for W2, a similar reason. It is harmonic outside Y and Z. Thanks. So it attains max at W2y, and a chance minimum at W2z. And W2x has to be between these two. And this shows that W2x is less than W2y. Okay, so this completes the proof that the left-hand side is less than the right-hand side. And this shows that the effective resistance satisfies the triangle inequality. Okay, I will stop here. And for the third class, it is the first recitation. And the recitation exercise is also on website, but I'm not sure whether you already signed it. Exercise sheet. Okay, this is the exercise sheet of today's recitation. I put it on the website, but maybe I didn't tell you.
I asked the assistant and he told me he was going to put it on Shamilo, so I thought it was going to be on Shamilo, but...
Okay, so now you can have a quick what's the question? So there are two questions. The first is about top to random shuffle. It is the last example we discussed in the second lecture. The second part is the simple random walk on Z. So, okay, I will stop here and the TA will come later.